Hello, everyone. Welcome. In this video, we will look at finding shortest path. We have the graph. So we'll pick one vertex and another vertex and find the shortest path between the two. Now, our algorithm this is the Dijkstra's algorithm. And this is going to find the shortest path from one source to all the others. It's the byproduct, and we want to find the shortest path between A and B, but if we use this algorithm, it's actually finding the shortest path from A to all the other vertices. All right, so let's look at this algorithm. So here's the input. It's the weighted graph and with non-negative weights. And the output, it's the shortest path tree with the source vertex S as the root. And we have this shortest path S. This is the let T be a set that contains the vertices whose paths to S are known. Initially, T is empty. Set the cost. It's very similar to the minimum spanning tree. We use this cost. Cost S is 0, and cost V is infinity. Now, why size of T is less than N, we're going to find U not in T with the smallest cost U. We're going to add U to V. But now, so please look at this. What is the cost? Cost is in the minimum spanning tree, and cost is V is the shortest edge to the vertices already in T. But now this cost V is the shortest path known from this V to the source. So that's the difference. All right, so we're going to add U to T. Now we're going to update V, not in T, all the edges adjacent to U. We're going to look at it to see if there's a need to update it because you added U to T. So consequently, and there might be some changes. There might be better, shorter paths and from the adjacent vertex of U and to the source. So that's what this is for. All right, so for example here, this is a T. All right, so here U is the smallest cost. So that means from U and there's the shortest path to S. Okay, and we're going to add U to this T. And now we may need to adjust the cost for V1 and V2, and because U is added to T. So here is an example here. Let's start from this 1. So 1 is this, the cost of 1 is now 0, all the others are infinite. So now we are going to add this 1 to T. So that's the first thing. So after you add 1 to T, so you're going to adjust the cost for 2, 0, 6, and 3. So all of this adjusted. All right, so now the smallest cost is this 5 here. We're going to add 2. All right, after you add 2, so look, the cost of 0 and now is 8, right? But after you add this one here, what would be the cost for this 0? It's going to be 6, 1, 5. So not 8 anymore. 8 is larger than 6. So now you see some changes here. So that's here. And now continue to look at the smallest cost is going to be this one here. So you have 1, 2 there. And now look at, and this is 0 is going to be smallest one here. So add 0. And now you're going to change the cost for this 5. 5 is 10. So this is the best here. Okay. And now we're going to pick 6 here. So 6 is 8. So that's here. Okay. And now we're going to have this either 5 or 3. So they're all 10. So pick 3. And now this is going to be, the next one is 5. And then, so this is 5, 8. So which one I'm going to pick? And look at the distance. This is 4, right now is 15. It's from here to here, it's 15. All right, so let's look at the implementation of this. The implementation of this, it's implemented, and here, show this path. So this is the shortest path, get shortest path for this starting vertex, and this is the cost or infinity except the source, and the parents are all -1, and this is the empty for t. And now, and we're gonna, if not all the vertices are discovered, and so we're going to continue to find the next one, u. So we're going to find the u and with the smallest cost and find it, add it into t. Now, please note that, and this is the, if not found, the bracket, if not found means graph is not connected. And now we're going to adjust the cost. See, adjust the cost, look at the cost. And so this is the age in the neighborhoods of u and e dot v, not in t. So look at the cost. If this, the cost is current one is greater than cost u plus this, the weight of this age. And now we're going to adjust this cost e dot v. And now it's going, because of the this vertex u is added to t, it may change the cost for its adjacent vertices. All right, so that is the implementation. And here is a test program, test shortest path. And so we're going to look at this here. It's the vertices and the edges. And now we create a weighted graph and with the vertices and edges. And so we get the shortest path and print all this. And so get the shortest path and with this vertex at index 11 and to the root. So here's another example here with different graph and vertices and edges and creating another graph. And so get the shortest path starting from vertex at index 3 and print everything. That is all for this section on finding shortest path. See you on the next video.